So we're going to move on to talking about putting energy to work. And we're going to talk about generating heat, a term called the heat capacity, look into what's called heat engines, and do some examples. So about 94% of the energy we use today comes from burning things. Okay, it comes from generating heat. And sometimes we just want heat, but we're going to learn now in the next couple of lectures how we can use it to, say, fly airplanes, propel cars, and light up screens. And here's just a list of some ways to generate heat, and basically getting more complex as you get up. So, first rubbing your hands together, basically any kind of form of friction, using sunlight, drying clothes outside, burning wood in a fireplace or stove, burn a fossil fuel for direct heat, right? So that's something that we do a lot of. Again, a lot of these we're going to talk a bunch about as we move on in the quarter. Run electrical current through a coil of wire that glows orange. This is like a toaster or a hair dryer or a space heater. Use electricity to run what's called a heat pump. We'll again talk about those. And then the last two are looking at nuclear reactions. Fission, which is where you split up a nucleus, and fusion, where you bring two atoms to form a bigger one. Right now, fusion is done in the sun. We are not able to actually do it here, but fission is something that we actually do use. And again, we'll talk about a lot of these as we go through the quarter. But this is, again, the ways we have for generating heat. Now, sort of talking about this, it's nice to start with just some general terms. And the first general term we're going to talk about is heat capacity. And we've already dealt with this, even though we didn't really call it that. But we learned that it takes 1 kilocalorie to heat 1 kilogram of water by 1 degree Celsius. And so this is the definition of what's called the specific heat capacity for the particular material you're describing. And so using this specific heat capacity, we can figure out how much energy it takes to heat a certain mass of whatever object to a certain new temperature. And so water is sort of the biggest one. So it's 4184, so 4,184, and so it takes that many joules. Again, that's our definition of 1 kilocalorie to raise 1 kilogram of water by 1 degree Celsius. So that's the units work out this way here. Sometimes we use a C for heat capacity, equals something kind of like this here. And basically what's happening is we're going to take this C and multiply it by how many kilograms we have and how many degrees we want to raise it in order to find the total amount of heat required to change something. Now this is one of those things that we're going to use a lot and will be probably sometimes a little bit sloppy. Like for instance, oftentimes in the book, instead of using 4184, we'll use 4,000, just because generally we're only looking for like a rough estimate anyway. And so let's do a couple of examples here. So first, let's look how much heat is needed to warm 50 kilograms of air to warm, say, a room in your house from an outside temperature of 0 Celsius to room temperature, which we'll sometimes call 20 degrees Celsius. So room temperature is generally somewhere between 20 and 22 degrees Celsius. This is something that takes a little bit of time getting used to because most of us aren't used to using Celsius to talk about temperatures. But 0 degrees is of course where water freezes, and 20 degrees is roughly room temperature. And so what we're asking is how much heat is needed to warm basically one of our rooms, assuming that we're in winter and it's 0 degrees outside, out to 20. And so the way we do this is, so we look here, air is, according to this, 1,005. And so just to be kind of rough, I'm going to call it 1,000 kilograms, joules per kilogram, joules per kilogram per degrees Celsius. Now, what this works out is we're going to multiply this by what? Well, the first thing is 50 kilograms. And so what that does is it cancels out the kilograms. We're basically just converting units. And then here, I want to raise it by 20 degrees. I want to go from 0 to 20. So I'm going to call it 20 degrees Celsius, which again cancels out that, and so the only unit remaining is the joule. And when I do 1,000 times 50 times 20, I got about a million. So 1 times 10 to the 6th joules. We'll usually use Q to talk about heat, and the book sort of doesn't like to use a formula here, but basically what this is it'd be that specific heat capacity times the mass you're talking about times the temperature increase you want. But again, you can also think about it over here as just sort of canceling out the units. All right, so that's our first example. Let's do another one, a little bit trickier. And so here we've got a 2,000 kilogram truck, and we said that it's transporting a 1 cubic centimeter container of water. How much energy will it take to raise the temperature of the whole ensemble by 5 degrees Celsius? So the first thing is, this happens in physics. There's words we use that generally don't use a ton in regular life. Here's one that's ensemble. So I Googled it to get the actual definition. It's a group of items viewed as a whole rather than individually. And so that's just the word physicists like to use. And so here we're talking about one truck and then the water. We want to know is how much energy it takes to raise both of their temperatures. And so again, we'll use the same sort of idea. A truck is going to be mostly steel. And so again, I'm going to be kind of sloppy with this and call the heat capacity of steel to be 500 joules per kilogram per degree Celsius. And so here, so it's a 2,000 kilogram truck. So I'll write that there, and then I'm increasing its temperature by 5 degrees. And again, the whole idea here is that we're canceling units. So the kilograms cancel, and then the degrees Celsius cancels. And when I did this one here, I got an answer of 5 times 10 to the 6th joules, which again you can write as 5 megajoules. And so that's how much energy it takes to raise the temperature of just the truck part. So now we'll focus on the water, and let's look at this. So here we've given some clues, because if we look at the water, so again, water is what? It's again, we'll use 4,000. We'll be kind of sloppy. 4,000 joules per kilogram per degree Celsius. So I want to raise it by 5, but I don't know what the kilogram is. We're told that it's 1 cubic centimeter of water. And so for water, 1 cubic meter is the same thing as what we call 1,000 liters, which is the same thing as 1,000 kilograms. And so this is just something that we sort of we'll use. And so if you can sort of talk about 1 cubic meter, 1,000 liters, or 1,000 kilograms as being equivalent. And so here I'll multiply by that 1,000 kilograms, and then 5 degrees Celsius. And so again, just like last time, the kilograms cancel, the degrees Celsius cancel. And when I did this calculation, I got equal to 20 times 10 to the 6 joules, or what we can call 20 megajoules. And so for the total energy, we just add up the two. So it's 5 megajoules plus 20 megajoules, and we get 25 megajoules. And just one thing to note here is that the water took much more heat to increase its temperature. If you see here on the chart, water has got one of the highest specific heat capacities, probably the highest that we'll generally deal with. And so it's really, it takes a lot of energy to raise the temperature of water. Just something to kind of note. All right, and so here's one that's maybe a little bit more complicated example. And so looking at home heating and cooling. And so this question is going to use a couple different concepts we've dealt with, and so let's dive in. How long will it take to heat up the interior of a mobile home from 0 degrees to 20 Celsius? So again, what we're doing here is we're rising it from freezing up to room temperature. So we're assuming that it's wintertime and it's really cold, and we want to heat up our home to room temperature. And to do that, we're using two 1,500 watt space heaters. So just, it's the kind of things you might buy at the store to heat up your room. And we're going to assume that we need to heat up 6,000 kilograms of mass. So basically in your room, between the air and the furniture and everything, it's about 6,000 kilograms of mass. Now, The textbook advises us that if it's a bunch of stuff, right, that a good estimate for the specific heat capacity is about 1,000. And so that's sort of assuming that it's mostly air. There's probably some furniture and other stuff, but that's a good kind of place to start. And so the first thing I would do with this one then is let's go through and figure out, how much energy do we need to heat that up to that exact temperature. So kilograms, degrees Celsius. And so that's our specific heat capacity for sort of a general room or something like that. And so we're told that we have 6,000 kilograms of stuff, and we're going to multiply by 20. So we're trying to raise up the degrees up to 20. And so again, kilograms cancel. We're just canceling units here in some sense. And so 1,000 times 6,000 times 20, and I got 1.2 times 10 to the 8 joules. Excuse me. Okay, so 1.2 times 10 to the 8 joules. And so that's how much energy we need to do this. Now, what we're told is we have two 1,500 watt space heaters. So what I want you to do is maybe just take a second and think about, how do I take this amount of heat? So this is energy. We're going to call it heat Q. And if I know that I've got two 1,500 watt space heaters, what do I do with that to figure out the time? So maybe pause, take a second, and we'll discuss. All right, and so what I'm going to do is, so this is joules, and so I'm going to start with this number, 1.2 times 10 to the 8 joules. Now, if we look at our space heater, right, so it's going to have 3,000 watts, because there's two of them. And what is a watt? A watt is a joule per second. And so if you look over here, what I can do is sort of invert that and think 1 second per 3,000 joules. And so basically this heater gives us 3,000 joules of energy every second. And so if I invert this, what happens here is the joules cancel out nicely, and I'm left over with seconds. And so I get, when I multiply 1.2 times 10 to the 8th divided by 3,000, I got 4 times 10 to the 4 seconds. Okay, so our answer is 4 times 10 to the 4 seconds. Now that's not super convenient, because when I think about that, I'm like, how long is that? I don't really know. And so what we will typically do is transfer this into something, when it's that huge, something else that makes a little bit more sense to us. And so what I'm going to do is I'm going to say that I know 1 hour, right, our big conversion is 3,600 seconds. So again, the seconds cancel, and it's 4 times 10 to the 4th divided by 3,600, and I got 11.11 hours. So somewhere around 11 hours is what it's going to take to heat up this room with these two space heaters. Now this is, again, how much energy we need to heat up this mass. But what we're not counting on is that the house loses energy. And so there's a little bit of a discussion on this. And I just wanted to kind of go through it just to kind of show us sort of how this is working. And so what we're saying here is that, so in a house you have windows and then just sort of regular things like walls and ceilings. And so what they're saying here is that we lose 0.15 watts per temperature difference for each square meter of external in-facing surface. So basically when there's a temperature difference between the house and the outside, you're going to lose energy. And it depends on this degrees Celsius. So for instance, in this case here, you've got some for the actual walls and ceilings, and then some over here for the windows. And so they go through and calculate, and it's basically looking at surface areas and things. And so what they come out with is basically for a house like this, a really well constructed one, right? You lose 75 watts. So that's basically 75 joules per second per degree of temperature difference. So again, this applies when the temperature inside the house is different than the outside. And then what they sort of say is, okay, so that's a really well done house. But then typical houses, or at least sort of a decently built one. This is one that was sort of built extremely well to keep the energy in. One that's sort of built decently well is about twice that. And then, unfortunately, most typical houses aren't built quite that much, and so are about double that. And so these are three things that we might use, throughout the quarter, again, just to kind of describe this, because this is something that's important when you're heating your home, is how much energy you're losing. And if you look here in this example here, what they're basically saying is that, okay, so for each of these, this again depends on the temperature difference. And so let's just assume again this temperature difference of 20 degrees Celsius. So again, maybe it's freezing outside, and inside you're at room temperature. And so if you take 75 times 20, you get 1,500 watts. If you take 150 times 20, you get the next one up 3,000 watts. And then finally, for this, the houses that we all typically live in, 6,000 watts. And so, that last example sort of said, okay, to get the house to the temperature, but that's not including what you might be losing. But of course, that's what happens every day, right? If you're heating your home, it's because you're losing this energy to the outside. And depending on sort of how well built your house is, we get sort of three different numbers. So the text uses this, and this is something we might go back to time. All right, thanks.